Good day, guys, and welcome to Intellect Academy. I welcome you all, and today we'll be talking on fluid mechanics. The topic is centrifugal pumps. First of all, before we go into this example, I'd like to enlighten you and define what a centrifugal pump is. First of all, we'll go by saying what is a pump. Now, we know that the normal importance of pump or the use of a pump is to increase the pressure of a fluid, which in this case is a liquid. Now, centrifugal pumps are pumps that are electrically and steam driven. This is a pumping system. You can say this is a pumping system. Before we go into the centrifugal pump, just know that this is a pumping system. This is not a centrifugal pumping system. This is a pumping system. In this system, you have where the pumping system is divided into two parts. We have the suction side, which is the part where the fluid flows in, the inlet of the fluid. Then we have the delivery side where the fluid, which is the liquid, flows out. So take note, there will be a pressure developed at this point in the section, which is the pressure of the suction or suction pressure. There will also be a head developed here, which is what? The suction head. Also take note that at this point, there will be a pressure developed at the discharge or delivery side. Also take note that there will be a head in this point too, which is called the discharge head. Now, take note that when we are going to solve this and bring out a mathematical expression, it will obey Bernoulli's equation. So from Bernoulli's equation, you know that you were to calculate the head of each of these cases. So take note that we have ZS, which is a suction head, where we know that the static head of every system like this is the height of the column where the liquid flows through, or in this case where we have the suction part to be the suction head or suction static head. So in the case here we have ZD, we will also have what? The discharge head. So take note of that. So all this is the expression for the representation of these parameters. So where we have Px, we're going to have the suction pressure. Where we have Pd, we're going to have what? The discharge or delivery pressure. Take note of this. So now let's write down the expression for the static and discharge head. Of course, now we have formulas all over the board, so we'd like to explain what this formula means. Okay, now we have our head. You can see you have H subscript S, which stands for what? The head at the suction side. Take note that in this pumping system, we have two sides. We have the suction side and we have the discharge or delivery side. So now there will be a head at each of those points. Take note that this is the head at the suction side. This is the head at the delivery or discharge side. So take note, this suction head is equals to the static head of the suction, which is static suction head, plus the square of the speed of that suction. Now take note, Bernoulli's equation is more of like, it's talking about the pressure of this fluid. We'll have the density, we'll have gravity acting on those fluids. We will have the speed of those fluids, and we'll have the head loss of those fluids. Is that understood? We will have those three parameters. For you to get the head at this suction side, take note that we had this ZX signifies this ZX or ZX and ZD, which is for this part. So we have ZX and ZD. This signifies the static suction head. This is the static suction head. Then this signifies the static discharge head. It's as simple as that. Then this signifies Vs, and Vd signifies this is the speed of that liquid. I told you that of a course of our study, centrifugal pumps is the function of a pump is to increase the pressure of a fluid. Of course, here we have this will be the speed of the fluid at this suction side. This will be the speed at the discharge part. Is that understood? So take note that we have this is the speed, signifies the speed at the suction side. This Vd signifies what? The speed at the discharge side. Then we have PS. Of course, in every point of a fluid in a system, which is in a pump, there must be a pressure at that point. So this PX signifies the pressure at suction side. Then this PD here signifies the pressure at discharge. So take notes, we have this is the pressure at the suction. We know what rho is. Rho signifies the density of the liquid. In this case, of course, it can be any substance. It can be a fuel, it can be diesel, it can be anything, it can be water. The density will be required. Of course, the density in each of these terms are constant. The gravity, of course, we know that in normal cases, gravity is taken as 9.81 meters per second square. So we know that the next one we have is the now take note, I said earlier that we have head loss due to different situations in a conduit or pipe or in a system, which is a pumping system. There can be head loss due to friction, which is the roughness of the internals of the diameter of the pipes or of the pumping systems. We can have head loss due to the bend of the pipe. We can have head loss due to contraction. We can have head loss due to many situations, enlargement. So this is the dynamic. So take note that HLS signifies the dynamic. This is the dynamic head loss due to friction. It can be anything, but in this case it's due to friction. Now take note, in this case it is negative. I want you to differentiate that in this case it is negative for what? The suction side. Then we have, this is for the suction side. Then we have HLD signifies the head loss in the discharge side. So there's a dynamic head loss due to each of these parameters I told you earlier. So now the next thing we're going to talk about is the total head loss. The total head loss is the discharge head minus the suction head. Take note that if you perform a kind of collection of like terms, it's going to be simplified to give you this expression. So we are having this total head equals to the static discharge head subtracted by the static suction head plus the velocity at that discharge side, the square of the velocity of that discharge side, subtracted by what? The square of the velocity of the suction part, all over 2 multiplied by gravity plus the pressure at the discharge minus the pressure at the suction, all over rho g, which is density multiplied by gravity. Then we have what? The summation of what? The dynamic losses. This is dynamic losses due to the discharge. This is due to the suction. So now let us start by attempting this question. Okay, now we are going to solve this sample problem on centrifugal pumps. Now first of all, we're going to write the given parameters. So we're having a centrifugal pump in a pipe system has the following operational data. Number one, we have the impeller rotational motion, which is given by N. So we have, first of all, we have our solution to the problem. So okay, let me use this marker. So we have solution to this problem. We are going to write our given parameters. So what are we given in this question? So first of all, we have an impeller rotating speed, which is given by 550 RPM, which is revolution per minute. So we have our rotational speed as 550 RPM. Then we have our loss in the impeller, which is given. So take note, this our loss in the impeller is given in Newton. So take note, it is given in Newton, we know that. So first of all, we're having the loss in the impeller is given by HS because it's at the suction, that's where the impeller is. So we're having 0.40 Newton. We're having the loss in an involute casing, which will know be HD is equals to 0.57 Newton. We are having the power required, which is power. So we're having power equals to 340.5 kilowatt. We're having the fluid velocity flow, which is 5.14 meters per second. Now take note, velocity, the fluid at inlet will be the velocity at inlet will be the velocity at the suction, because inlet signifies where the fluid flows in. So we're having Vs will be equals to, we have this as 5.14 meters per second. So we have this as 5.14 meters per second. So obviously we're having the delivery velocity, you know that this is where the discharge velocity. So it's given by 4.22 meters per second. So now they say that if the pump and the piping system delivers 0.26 meter cube per second. In our last video, I told you, I explained a situation where you have volume over time, which we say that is discharge. So we are having discharge Q is equal to 0.26 meter cube per second. Now, with an overall efficiency of 70%, so we're having the efficiency overall given by this equals to 70%. Okay, take note of that. So now say determine the static head. So take note, we're looking for the static head. So we are looking for the static head H I. Take note, this static head is going to be known as the head, the rise of the head, which is more of like the, okay, is given by this expression PD minus PS over rho G. Take note that anywhere you see this, you replace this as what? The static head. So this is going to be known as the static head. Then we're going to look for the total head. So we're looking for this parameter. Let's put a question mark there. We're looking for the total head. Look for the total head developed by the pump. Of course, we're looking for the shaft power input. So we know the efficiency is output over input multiplied by 100. So if you notice, we have the output here. So we're looking for the shaft input. So I can give you a small understanding when we get there. So we're looking for the power shaft input given by the shaft power input. So let's call it VI. Then I'm looking for what? The specific speed of the pump is given by a formula. So when we get there, we'll cross it. Okay, now so we're looking for these parameters. So first of all, we'll start by generating the formula for Bernoulli's equation. In this case, we're going to change some parameters because we have power here is going to be included in the question in this Bernoulli's equation. So we're going to see how we do that. Okay, now let's go there. So now in this case, we need to write down Bernoulli's equation. So we're going to say applying Bernoulli's equation. So applying Bernoulli's equation. So So we have so when you apply Bernoulli's equation, we're going to have, so Bernoulli's equation is more of like, in cases where you have 2 points, let's say we have 2 points like this. Let's say this is point A, this is point B. In this case, this will be point S and this is point D. Okay, now so we are going to make HI subject formula from this case. So we have this as HI. When we move this to this other side, we're going to have negative VD square negative VS square all over 2G. When we move this to the other side, we're going to have HLD plus HLS. When we move that to the other side, we're going to have W over M over G. So now, what we're going to do is we are going to compute our value. So we are going to have, for VD, we know that VD is given by 4.22 square negative VS is given by 5.14. So we have 5.14 square over 2 multiplied by 9.81. This is going to be all negative. HLD, which we have here, is equals to 0.57 plus 0.40. Then now take note that everything you see here is going to give you the power. So we're having the power as 34.5 over G, which is 9.81. So when we do the arithmetic operation, so we're going to have 34.17 meters. So take note that this is the static head developed by the pump. Now take note, this static head, we said that is what? PD negative PX over what? Rho G. Now let's look for the total head. Take note that this term, the total head is given by this expression, W over M over G. So the total head is given by this expression. So when we do that, we're going to have this as 340.5 over what? 9.81. We'll have this as 34.71 meters. So the total head is given by 34.71 meters, where the static head is given by 34.17 meters. So take note that this is the static and this is the total head developed by the pump. So we have calculated this and we are given this is 34.17 meters. We have gotten this to be 34.71 meters. So next off, we are looking for what? The power shaft input. So from there, you know that efficiency is equals to output over input. So multiply by 100. So take note, in this case, the power required by the shaft is going to be the power output. Then the power input of the shaft is given by this input you have here. So when we make this input formula, we're going to have the input shaft is going to be what? So when this comes here, you're going to have the output over what? Multiplied by 100 over what? The efficiency. So when we do that, we're going to have this as 34.5 all over 70 multiplied by 100. So we're given by 486.73 kilowatts. So this, take note that this is what? The power input by the shaft. So take note, it's as easy as this. The output is this value you're given. They are looking for the shaft input. Now take note, this is the power required by the shaft. This is what? The shaft output. So the shaft power input is given by 486 86.73 kilowatts. Take note that efficiency is what cannot be 100% because of the head loss. There will be almost energy loss. There must be energy loss, which you can see that there are losses here, which are the dynamic losses in this case. So let's look for what the NSS. Okay, now next we have to calculate the NSS, which is known as what? The specific speed, or what? The suction specific speed. Now this can be calculated in terms of another parameter. So the NSS is given by the rotational speed, which is in RPM, which is in this case is 550 RPM, multiplied by the discharge all over what? The gravity multiplied by NPSH all over 3/4, raised to power 3/4, raised to power 3/4. So in this case, this NPSH is known as what? The total pressure of what? The suction head. It's more like total suction pressure. So this can also be given as N square root of Q, which is the discharge, multiplied by the total head raised to power 3/4. Take note, the total head is what we calculated here, which is given by what? 34.71 meters. Is that understood? That is the total head. Take note that this total head is the same as this. So therefore we have the discharge given by 0.26 meter cube per second. We have the rotational speed, which is 550. So we are going to work with this. If we are given the NPSH, we will calculate in terms of this parameter. So what we're going to do is we're going to substitute formulas, and we're going to solve this, and we're going to move. So we're having NSS, we have this as 550 square root of 0.26 over 34.71 raised to power 3/4. Perform an operation here. You're going to have 19.62 RPM. So take note that we have calculated the power earlier, and we got the power to be 486.73 kilowatts, and we just calculated what? The suction specific speed, which is the specific speed. We got this value as what? 19.62 RPM. So this is all for the sample problem of centrifugal pumps. In our next episode, we're going to solve another example, which is going to give you an overview of problems involving centrifugal pumps. So if you know this video was very beneficial to you, please like, share, and subscribe to the YouTube channel. Thank you very much.